Welcome to the second part of the problem-solving sessions for Chapter 31 and 32. We begin where we left off with question 5. Question 5 shows us a figure, and it says that there is a bar, a conducting bar of length 1.2 meters that can slide without friction along the rails that are given here in the presence of a magnetic field which is pointed perpendicularly downward. So in other words, there is an external magnetic field that cuts through this system, the rod and rail system. But of course, we are not interested in this side because this is not a closed loop. This is open. We are only interested in what is happening here. So this is our external magnetic field. And we can see also that this external magnetic field is parallel to the normal that this area defines. And so we know that our angle theta, when we consider it, will be 0 degrees. Now, there is a resistor which is connected along this closed circuit, and the value of the resistance is 6 ohms. The bar, we're told, is sliding to the right at a constant speed of 2 meters per second. And the first thing we're asked to do is to calculate the EMF and the current which is induced in the circuit. Well, we know that this region, this dimension of the area is increasing because the rod is being pulled to the right. And so if we just consider first the changing magnetic flux, and we can go ahead and look at the time rate of the changing magnetic flux here, it's going to be equal to the magnetic field, which itself is not changing, times the changing area with respect to time, and that is what is happening. The area is changing, but only one dimension of the area, times the cosine of 0, which is 1. And so let's say more specifically, the EMF will be equal to the negative change in the magnetic flux, and of course our N is equal to 1. So we just put a minus sign here for our EMF. And let's see, we have minus B. The area is made up of L times W. But our W is our width, and in fact, I'm sorry, let me go ahead and call that X, because it'll just be simpler since we define this as X. So X is what is changing in time, so we pull L out of the derivative, dx over dt times 1 because of the cosine of 0. And the EMF, therefore, is equal to minus B times L times V. And so to calculate the EMF, we substitute our values. Our B is 2.5 Tesla. Our L is 1.2 meters. And our V is 2 meters per second. And it's a constant. When we multiply it all out, we get 6 volts, negative 6 volts. The current will be given by Ohm's law, where we now only consider the magnitude of the EMF. And so that magnitude is 6 volts. The resistance is 6 ohms. And so our current here is simply 1 amp. In part B, we're asked to calculate the applied force necessary to slide the bar. And let's just see if we can make an application here using Lenz's law to get some directions. Now we know that as more and more of the area is being open to this external magnetic field, there's going to be an induced magnetic field to oppose this more and more of these magnetic field lines cutting through the area. And the induced magnetic field will be in the opposite direction, which for us here is positive k hat. If we use the right-hand rule from chapter 30, we find that the current which is flowing when k hat is, when the direction is positive k hat, is counterclockwise, which means that it flows in this direction. Well, we've got a current that flows upward along the rail, and now we're just going to go ahead from chapter 29 this time and look at the magnetic force on this current due to its presence in this external magnetic field. Well, our current is in the positive j hat direction. The external magnetic field is in the minus k hat direction. And if you recall, FB, chapter 29, was equal to I times L, and this is going to be our L here, cross B, where B is the external magnetic field, not the one which is induced. The I we just calculated is 1 amp. L is 1.2 meters. And the direction of L is in the positive j hat direction. And we're going to cross that times the external magnetic field, which is 2.5 Tesla. And we said that it was in the minus k hat direction. And what we get here is that the magnetic force, therefore, j hat cross negative k hat gives us a minus I hat direction with a magnitude of 3 newtons. Well, let's see. Let's come up here, which means that the magnetic force is in this direction, FB. But because this rod is moving at constant velocity, see, this is constant, that means that the magnitude of FB must equal the magnitude of the applied force. Well, they've asked us to calculate the applied force, but since we have a way to calculate the magnetic force, the applied force is going to be equal to positive 3 newtons in the, of course, this time positive I hat direction. Okay, let's come back up here. Lastly, they want us to determine the rate at which energy is being supplied to the resistor. Well, we know that the energy supplied, the rate of energy supply, is the average power, and we can calculate it in 2 ways. If we know the applied force, we can take that, dot it with the velocity. The applied force is 3 newtons in the I hat direction, and we're going to dot that by the velocity, which is 2 meters per second, also in the I hat direction. That gives us 6 watts. But because everything must be related, we could also calculate the average power as the current, the induced current squared times resistance. Well, we found that the induced current was equal to 1 amps. 1 amp squared times the resistance of the resistor, which is 6 ohms, also gives us 6 watts. So no matter which way we choose to calculate, we consistently get the value of 6 watts. How about if we take the current times the EMF, which was induced? So the induced current times the induced EMF, the induced current 1 amp, the EMF that was induced had a magnitude of 6 volts, and here again 6 watts is the value of the power that is supplied to the resistor. Next question. In question 6, we are told that there is a metal ring which has been placed so that there is a solenoid that is directly in front of the ring. The solenoid is attached to a battery with a switch. The positive terminal of the battery supplies a current to the solenoid, which will flow in this direction here. And so you can see that we've got current goes up, comes down. We've got current this way, current this way, current this way, current this way. And using the right-hand rule, when the current through the solenoid is in this given direction, right-hand rule tells us the magnetic field of the solenoid, which is external to the ring, it points to the left. So I'll go ahead and just draw it here. That's the external magnetic field with a north pole that points to the left. Now, they've shown that the switch is open to start with, which of course means that there will be no current flowing through the solenoid and therefore no external magnetic field. But they ask us to determine the direction of the induced magnetic field and the induced current in the ring at the following situations. First, at the instant that the switch in the circuit is closed. Well, at the instant that the switch is closed, the current is growing in size, and so is the external magnetic field. Well, this ring does not like to see an external magnetic field which is growing, so it produces an induced magnetic field in the opposite direction. And what that means is that there is going to be a current that is going to flow through the ring by the right-hand rule. That current is going to flow in this direction here, which if we're facing this ring, we call that in the clockwise direction. Okay, so when the switch is first closed, there will be a current that flows in the clockwise direction and an induced magnetic field that points to the right. Well, the next instant they want us to calculate the induced quantities is after the switch has been closed for several seconds. Well, when the switch has been closed for several seconds, there is no change in the external magnetic field, and therefore no change in the magnetic flux which cuts through the ring. Well, in this case, if there's no change in the magnetic flux, there's no EMF, there is no induced current, let's go ahead and put that as 0, and therefore no induced magnetic field since there's no induced current. So this is in the case of 1, this is in the case of 2. How about the last case, which we're going to call case 3, and we're just going to switch colors to make it easier. At the instant that the switch is open, well, when the switch is first opened, the external magnetic field is getting weaker. When the ring sees that, it tries to produce its own induced field to prevent the weakening of the external magnetic field. So it lines up with the external magnetic field. And of course that then, using the right-hand rule from chapter 30, we see that we then end up with a current which, if we're facing the ring, will appear to be counterclockwise. So this is the case in number 3 when the switch is first opened. And of course, this problem is strictly Lenz's law, an exercise in Lenz's law, and so will the next couple of questions that we're going to address. So let's go to the next question. Let me get the green back. Here we see that there is a rectangular metal loop of dimensions L, W, and there is a region where there is a magnetic field that is about 3 W's wide. So in other words, if you took 3 times the width of this loop, this is the region where there is this magnetic field. And the in part here just means that it's into the page. In other words, in the minus k-hat direction. So don't let this confuse you with the word induced. This definitely is an external magnetic field to the loop. Now the loop is moving to the right at a constant speed, and we're asked to determine the graph of flux with distance as well as EMF with distance. So let's see what happens. Well, the graph has been drawn here for us just to simplify the picture. And what we have here, the 0 corresponds to the right-hand part of this loop. So before ever this loop enters the region of the magnetic field, you see there's no flux that cuts through because there's no line. So this would be the case. Let me just take it back, where this happens to be the loop. It has not even entered the field yet. So no flux, no EMF. Now it begins to enter, so this is now, let's call this position 1, which means it's this right here. And I'm going to just go ahead and get my eraser out to get rid of the green so that we don't get that confused. This is position 1, where you can see that the loop went from no magnetic field lines cutting through to magnetic field lines cutting through. Here is the magnetic flux increasing as the whole of the loop penetrates, okay, as it's moving in. And the EMF, of course, because we, by Faraday's law, take the EMF as minus n, change in the magnetic flux with respect to time, and that change is, of course, given by, the slope of this line. This is the changing flux with respect to time. The EMF, which is produced here, is shown as the negative BLV. And of course, the negative BLV came from the example that we just did earlier, where you saw that the area was increasing, more and more lines were cutting through the circuit, the loop, and the speed at which this loop is entering is what we call V, which is dx over dt. L is just the dimension which doesn't change in the area. Well, now the loop has fully penetrated, and you can see that the flux is constant. Why? Because the same number of magnetic field lines cut through it. Our EMF is 0 because our flux is not changing in time. See, we have a horizontal or a 0 slope line. Now we begin to exit the region where there is a magnetic field, so the flux is dropping off. Well, this would be region 3 right here, which is this one. And by the way, this is 2, which is this one right here. So we've got 3. Our magnetic flux is now dropping off as this loop fully exits, and in this case, again, because the flux is negative since it's dropping off, our EMF will be positive because of that negative sign, and once again we have our EMF because our magnetic flux is changing in time. Well, the next problem will actually ask us to do the same thing, but this time we are going to, as this ring moves in these 5 different positions, to determine the direction of the induced current and of course, the induced magnetic field at these 5 points in time. Well, we start out with the situation where the ring has no flux through it. Well, no magnetic flux also means no changing magnetic flux. No changing magnetic flux means that there is no induced current and therefore no induced magnetic field. So this is position 1. Now in position 2, you can see that we're changing the magnetic flux so that before no lines were cutting through, now we have at least one line cutting through. And now we're going to have an induced current and therefore an induced magnetic field. The question is, in which direction is the induced magnetic field going to point? Well, it tries to resist this changing flux. So it tries to block out this magnetic field going in by creating its induced magnetic field going out, see, in the opposite direction to prevent this change from occurring. And if we use the right-hand rule for determining the induced direction of the current when the induced magnetic field comes out, we find out that the current is going to be in the counterclockwise direction. That's, again, is our chapter 30. In number 3, we have a constant magnetic flux, which means that there's no change in it, and therefore the induced current and the induced magnetic field do not exist, in other words, equal 0. In position 4, the magnetic field is getting weaker, there's less lines cutting through. The induced magnetic field tries to prevent this reduction by lining up with the external magnetic field. See, this is the external magnetic field. External here. Again, to get the direction of the induced current, we use the right-hand rule from chapter 30, and we find that the induced current is in the clockwise direction. In position 5, nothing is changing, therefore the induced current as well as the induced magnetic field are equal to 0. So this basically is a sort of follow-up to the previous problem that we did, but this time taking into account those given directions. Let's go to question 9, and we'll end this session basically at question 9. In fact, question 9 is really 2 different questions. The first part, which we'll do, so let me put a line through because these are 2 different scenarios. We have a coil with a resistance and no battery, nothing connected to it, but there's a long wire beneath it that carries a current. And the question is, what is the direction of the induced current through the coil with the resistor R when this current right here, which is external to the coil, is increasing? Now, the first thing we want to know is what is the direction of the external magnetic field that cuts through this loop. Well, in chapter 30, we saw that the direction would be above the wire. The direction of the magnetic field is into the loop, and below the wire, it's out of. But we don't care about the below part because that doesn't cut through the loop. We only care about the above part. So this defines the external magnetic field, which cuts through the loop. Because the current is increasing, so will the magnetic field. Well, the loop tries to prevent that increase by creating an induced magnetic field that is opposite that of the external. So whereas the external was into the plane of the loop, the induced is out of the plane of the loop. And if we use the right-hand rule from chapter 30 to determine the current that's associated with a field in the positive k-hat direction, we find that the induced current is going to be actually in the counterclockwise direction. Okay, the next part here, which has nothing to do with the top part, says we have a ring, a conducting ring, and the magnet is falling through it. What is the direction of the induced magnetic field through the ring, as well as the induced current, in the case where the magnet is above the ring, and in the case where it has fallen through and the magnet has moved below the ring? So let's go ahead and just put the magnet when it's below the ring. Well, as the magnet is approaching the ring tries to prevent, let me go ahead and get the red color here. The ring tries to prevent this approach and produces an induced magnetic field with a north blocking this external north. If we use the right-hand rule, we find that the current, if we're looking at the top of the ring, the current is going to be in the counterclockwise direction. When the magnet has fallen below the ring, then of course what the ring sees is that the external field is getting weaker, and so it tries to line up with the external field by producing an induced magnetic field with its north pole closest to the south pole of the external field, in other words, to try to attract it back. If we use the right-hand rule here, what we find is that the direction of the current is actually in the clockwise direction. So this is what happens when the magnet is below the ring, and this is what happens when the magnet is above the ring. All applications of Lenz's law. Well, this concludes the second part of the problem-solving session for chapters 31 and 32. Until next time.